However, Alice and Bob are, as you remember, pretty good quantum physicists. So they do know that the classical physics and classical theory of information is not the end of the story. So now they think about the following scenario. They say, well, maybe. We don't know what the devices are doing. Nobody told us. But maybe those devices, those boxes have qubits embedded somewhere in the memory, and those qubits are entangled across the devices. So perhaps Alice and Bob share entangled pair of qubits, and whenever they choose to the settings and press the button, effectively they perform the measurements on those qubits. So then consider then the scenario where it is indeed the case, and suppose that A0 corresponds to the say the X measurement, and A1 corresponds to the Z measurements on the Alice side, and here B0 corresponds to the measurement that is described by the observable 1 over square root of 2x plus Z, and B1 will be equal to 1 over square root of 2x minus Z. And then let's assume that whenever, for each measurement, for each act of choosing the setting and pressing the button, the measurement is performed on qubits, and the two qubits that one on the Alice side and one on the Bob side are in the maximally entangled state. So they are in a state 1 over square root of 2, 0, 0 plus 1, 1. So that is the state, we call this state, we call it omega, right? Okay, so what will happen in this particular scenario? So what we have to do is to calculate the expectation values of correlations that we expect to see. So for example, we can calculate A0 tensor B0, the expectation value in this particular state. So I should perhaps write it as omega, and let me just put omega here. So let's do the calculations for at least one of them, right? So that would be the X, so that it would be the state omega, and I will have A0 is equal to X tensor 1 over square root of 2 X plus Z, and that is in state omega as well. So this is equal to 1 over square root of 2 omega X tensor X omega plus 1 over square root of 2 omega X tensor Z omega. Now we already know that in this maximally entangled state, this average value X tensor X is equal to 1, and this one is equal to 0. So the correlation in this case is 1 over square root of 2. And you can easily do evaluate the remaining three quantities, the correlations, and you will see that they are equal to this one we already evaluated, right? So it's 1 over square root of 2. The other one will be also 1 over square root of 2. This one will be also 1 over square root of 2, except this one will be equal to minus 1 over square root of 2. Okay, so then when Alice and Bob run the statistical test and choose randomly between A0 and 1, B0 and B1, they will then evaluate the average value of S, and it could be, in the quantum scenario, that this average value of S is equal to, you can see that this is going to be 4 times 1 over square root of 2, so that is equal to 2 times square root of 2. Oh, well, which is certainly more than 2, right? So, surprise, surprise. You can see that in the quantum world, we can go all the way to 2 square root of 2. We cannot go to 4. In fact, it can be proven There is another name associated with the upper quantum bound. It's Boris Cyrelson. It's called Cyrelson bound. Any help that you get from quantum theory, from entanglement, will not generate anything better than 2 square root of 2. And in fact, whenever you see the 2 square root of 2 for factor s, there is a very strong statement that no matter how those devices are constructed, if you run the statistical test that I just described, and you see the value of s equal 2 square root of 2, there's no other way to do it but just do it on qubits and just perform this kind of measurements. So it's kind of rigid stuff. If you see it, then you know there was just no, according to the known laws of physics, there was no other way of implementing this but just implanting qubits to the boxes and setting those knobs in such a way that A0 corresponds to the measurement of X and A1 to the measurements of Z, and correspondingly for B0, B1. So up to some local unitaries, but essentially up to some local isometries, it is this kind of physics behind. So from at least crypto point of view, this thing is actually extremely interesting because it means that those devices couldn't be pre-programmed. So the only way you can get this kind of correlations that goes to 2 square root of 2 is if there are genuinely qubits in maximally entangled state of this type in those devices. In which case, if this is the case, Alice and Bob can take advantage and distill the quantum key from that device. That would require to modify a little bit settings so that you have perfect correlations. At least you may just add one extra setting to say B2 equal to X and ask Bob to choose between B0, B1 and so 1 for which they get the perfect correlations. But that's actually a pure technicality. What I want to show you here is that even though you cannot get those magic correlations, quantum theory will tell you, will take you from 0 to hero, to square root of 2, which is way above the upper bound that is that corresponds to any classical correlation. So classical means pre-programmed, those values are there, probably known to someone, so therefore whatever outcomes you see, probably they just compromise, so there's no security in them. You go above 2, and if you go as far as 2 square root of 2, especially if you're just hitting square root of 2, then you know there's just no way to pre-program those boxes. So the only way to get this kind of correlations is to implant entangled qubits into the devices. And if this is the case, we can get the secure key. Of course, you know, again, in real life, you're never hitting 2 square root of 2. There's noise, you'll be somewhere there. And really sort of the hard work starts here when you have to just take some values which are smaller than Cyrelson bound and try to use all crypto techniques to evaluate how much information an eavesdropper can possibly have if you are somewhat below that Cyrelson bound. And is this amount of information dangerous, and can you use some cryptographic techniques like error correction, privacy amplification to get the secret key that is a bit sort of shorter than the one that you generated with this kind of noise. But that's you know, that's classical crypto essentially, and that is something that I'm not going to discuss. It's beautiful mathematics though, so I encourage those of you who are interested in that kind of stuff just to look it up. So that kind of concludes the very gentle and very sort of sketchy introduction to device independent scenario. You can see that in this kind of scenario, Alice and Bob get devices. They get devices from some external sources. They don't have to trust. There are, of course, assumptions. We assume that there are not embedded transmitter in those devices that will just transmit the outcomes to the external world. device-independent scenario is actually more useful when you try to correct for imperfections which are the result of the production. So it may be that you want to produce those devices yourself, but you're not kind of fluent in all the engineerings and all nitty-gritty details, and you're not so fluent with a screwdriver, right? So then you may goof something and you're not even aware that you did that. So that would be dangerous. But somehow this scenario protects you against all mistakes that you can make during the design and manufacturing process, which is probably more important than sort of more outlandish scenario in which you sort of accept those devices from an eavesdropper or a third party that you don't trust and use them. So device independent is a challenge. It's a really challenge to implement because all those conditions have to be satisfied, and you have to have sources of good entangled particles, like good entangled photons, and then the detector efficiency has to be good enough. There are all kind of attacks that you can think about on the device-independent scenario, but we have trust in our experimental colleagues, right? So they will get us there at some point, in which we will have a wonderful new world of the device-independent quantum cryptography.